Okay, this is our um, video from Dry Mix, Variables and Patterns. If you recall, we wrote a song called the Dry Mix song, and that is coming to our website, and it will help you remember the dependent variable is the reacting variable or the responding variable, and it goes on the y-axis, hence the word dry. And then the mix is the manipulated variable, independent x-axis. So the manipulated variable is the variable that's being used to tell us information about the other one. The dependent variable depends upon the independent variable, and it goes on the x-axis. All right, we'll look at that some more. But just remember dry mix, and you should be great in setting up your variables on the correct axis. It's very important to graphic. So let's look at an example of a problem here. This is out of our ACE homework. Use a table to write an equation that relates lunch cost L and number of riders N. Okay. Well, we're looking at our table here. I see that one rider costs $4.25. 5 costs 21, 25, 15, so on and so forth. The table skips some riders, but I think I can figure out what's in between. Use your equation to find the lunch cost for 25 riders. All right, so we need to develop our equation first. So, let's think about this. 10 riders is $42.50. 5 is $21.25. Well, the most obvious thing that I see is one rider is $4.25. So for any amount of riders, in our case here we're looking for 25, we're going to have to use the letter N. So we'll start with that, N. And how much is one rider? Well, one rider costs $4.25 N. So let me rewrite that a little bit neater. And we have to solve for, when you have to ask yourself all the time, what am I solving for? Am I solving for riders? No, I know that. I know that I can have any amount of riders. I want to know how much it costs for any amount of riders. So if I have 58 riders, how much is that going to cost me? And we're using L to represent lunch cost. So L equals 425N. So now I can just take my 5, plug it in for N, and test it. Yes, 5 times 425 is 2125. Or I could take my 10 and plug it in and test it for N. Yes. Or, like the question asked me, I'll take my 25 and I'll plug it in to N. So now we have L equals 425 times 25. And remember, we're not going to use a multiplication sign for multiplication, the X or the dot or anything like that. We're just going to use parentheses. All right? So 425 times 25. If you have a calculator, do that real quick. And on mine, it says L equals, for 25 people, $106.25. Okay? If you ever have trouble developing your equation, always start with, what am I solving for? Am I solving for, in this case, lunch costs, or am I solving for riders? And that just helps you determine the other variable and what number goes with it and what's happening to it. Okay? So now let's see, let's kind of do a reverse type operation here. How many riders could eat lunch for $89.25? Well, one instinct would be maybe I could just extend my table from 15 to 16 to 17 riders and see when I get to 89.25. But I think there's a better way. Let's use our equation. Equations are our friend. Don't be afraid of them. Use them. Use the equation. All right, so let's rewrite our equation. L equals 425n, right? Well, in this case, we know what L is. We don't know what N is. It's kind of backwards from what we're used to. So I'll replace my L with 8925. That equals 425n. Well, now what do? I got to get rid of that 425. I got to get n by itself so I can see what n equals. Just like up here, I have L equals. I need to know what n equals now. So how do I get rid of this 425 as being multiplied to the n? You have to divide it. Opposite operation. So the opposite of multiplication, which is happening right here technically, I need to divide it away. So I'll divide 425 away. And that cancels that. But whatever I do to one side, I have to do to the other. The golden rule of math. So 8925 divided by 425 should equal n. Well, so let's see what that is. Punch that into my calculator. 8925 divided by 425 equals 21 riders. So n equals 21 riders. Well, now we get to make a graph. We're going to graph our data. So we're going to use our dry mix phrase, and we're going to come up with, first of all, we need to know where do our variables go. Which one was depending upon the other? Did lunch cost depend upon the riders, or did riders depend upon the lunch costs? You could make an argument for both, but I think looking at it as lunch cost depends on the number of riders would be most appropriate. You want to know how many people you can take with you and how many that you do take, how much is it going to cost me? So let's put lunch costs as the dependent variable. So I'll write it right here. And we'll make the independent variable, our x variable, riders. Okay. And we also need a title. So don't forget your title. So we got our labels. Let's get a title. Let's call this riders lunch costs. Very original, I know. Very creative. All right, the next thing that we need to do is have an appropriate scale. We need to have the right intervals that make sense. So let's go back to our table. I'm going to erase some of these lines so that we can look at our table nicer. And we could go up to maybe 10 riders, and that's going to go up to $42.50 in cost. Well, we know we can go up to at least 20. So let's go up to 20 riders. 20 times 425. Let's do that. And that will be $85. All right, so we'll go up to 20 and $85. So let's go back to our graph. And we'll go up to $85. So I have, let's see, I'm counting up my y-axis, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll just make each one worth 10. So start at 0, always have to be 0, and then we have to use the same spacing the whole way. And that'll be 100, but I don't think I'm going to get there. And lunch cost, this is in dollars. Number of riders. We said we wanted to go up to 20 riders. So let's count how many I have here. I have 1, 2, I'm counting like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Well, we'll just call that 10, and we'll go, every line is worth 2. So this is 2 riders, 4 riders, 6 riders, 7, what am I doing? 6, 8, 10, 12, 14, 16, 18, 20 riders, and we'll stop there. If I have 0 riders show up, I have 0 lunch costs. Nobody's going to charge me anything for that. We know if I have 1 rider show up, it's $4.25. 2 riders showing up would be how much? Would be what, $8.50? So somewhere right around in here maybe. 4 riders. In fact, I'm just going to jump ahead to go to 10. So I'll go back to my chart and see where I'm at. 10 was $42.50. 5 was $21.25. I'm going to cheat a little bit. We'll go to 6. $25.50 for 6 and $42.50 for 10. So $25.50 and $42.50. 6, $25.50, halfway. 10 was $42.50, just about a fourth of the way. Okay, and I can already start to see my graph develop. I knew that at 20 was $85. I already did the math prior to this, so there we go. And I bet if I connect the dots, I'm going to have a pretty straight line. No, I'm not perfect here. That's pretty good. So, and then all my data is going to fall in between. And then a big question becomes, should I or should I not connect the dots? This is a great debate. If we connect the dots, we're saying that there's continuous data between the points. But we know we don't have continuous data because you can't have 1.35 riders or 10.7984 riders. That would be gruesome if that was possible. And we're not going to deal with that. But for the sake of keeping it visually nice looking, we're going to connect the dots from now on. As long as you understand that there is not, you can't have 4.5 riders. Just know that as you connect the dots. Okay? So that's how we would graph our data. And that looks nice. That makes sense. Yeah, as riders increase, our cost should increase. All right, next thing we need to do is an important concept of matching the graph to the situation. So I'm going to read through these situations here, and I'll give you a moment to do that. Okay, so let's look at the first situation described. The bicyclist took off and eventually had to stop for a flat tire. Then, to make up time, he pedaled faster. So we're going to, first of all, think of our 2 variables and what would they be and where they go. I think one would be time, for sure, because I see time right here. And then probably going to be distance. We're probably going to be looking at his distance or his speed. What do you think? Probably distance. And I'm going to guess it's A, because the key that I see is that he had to stop. And A, right here, stops. Flat. Nothing's happening. Time is continuing on, and he is doing nothing. Shaking his tire, but we don't see that in the graph. So he increases, but then he goes faster, and we see that by the steeper part of the graph right here. He's going faster. He's covering more ground in less time. So I'm going to match 1 to A. So I'll just put an A there with it. Situation number 2, as the store owner raised his price, he made more money per item, but eventually made less profit because it became too expensive for his customers. So he's making more and then starts to lose it. So I'm thinking he's got price and profit as his two variables. And I think it's going to be C. He gains some and then he loses it. So we'll put price here, profit over here. And as his price increases, you can see it going this way. As his price increases, when he's got a very low price, he's going to have a lot of customers. And they're like, yeah, we like this. We'll buy this. We'll buy that. And then it starts to hit the ceiling. Yeah, I don't know. That's getting a little expensive for the price here as the price gets over in this area. And then less and less people are willing to buy it. And eventually, you've got one poor sap down here who's probably willing to pay a very expensive price because he's got money to burn. But if you only sell one of those items a year, I don't think he's going to make much profit having all those others sit on his shelves, not going anywhere. So let's put C with 2. All right, third one, the runner took off at a really good pace, but eventually got tired. Which one looks like a slowing down pace? And again, we need to think of our two variables here. I'm thinking it's going to be time and distance again. Time, distance, D makes the most sense to me. And he's got a really strong pace right here, but eventually he's tired. Starts to wear out. He's covering less distance. It's taking him longer to do it, so his speed slows down. And then the last one, it must be B, but let's look at it. The skateboarder's speed as he went up a long hill. Well, as you know, if you go up a big hill, and especially on a skateboard, it'll be very difficult. Going up a large hill, you're going to start to go slower and slower and slower, especially if the hill gets steeper as you go, because your legs are wearing out. You're going to start to get exhausted. So I'm thinking B is probably the best option for that one as well. And it's the last one. All right, so again, I want to come back to dry mix here and look at this dependent reacting y-axis. So the dependent variable is the one that is relying upon the other one to make it change. And then the other one is doing the changing. It's the manipulated word. That's a tough word to say. So manipulated is changing. It's the one we're using. Just like you manipulate somebody, you use them to change the dependent variable. And it goes on the x-axis. So if you can remember dry mix, I think you'll be in good shape. That is the conclusion of our variables and patterns graphing video. Hopefully this helps. If you have any more questions, just please post them on Facebook or email RITT_SHIPPER @tccsa.net. That concludes our video.